Welcome. So in this video I want to talk about trigonometric functions and briefly discuss their derivatives. Let's start with a unit circle centered at the origin. We'll call that unit circle the trigonometric circle. Consider an angle whose initial side is the positive side of the x-axis and whose terminal side is the line segment in red here. Consider this right angle triangle here. The opposite side here is the sine value of the angle. Why is that? Well, it's because the sine of the angle is opposite over hypotenuse, but the hypotenuse is 1. So we just end up with the opposite side being the sine value of the angle. Similarly, the adjacent side of the angle is the cosine value. So if you consider a point P that lies at the intersection of the terminal side of the angle and the unit circle, its x-coordinate is cosine and its y-coordinate is sine. So on the trigonometric circle, we will define the sine and the cosine of an angle by being the y and the x-coordinate of the point, the corresponding point that lies on the unit circle. The advantage with this definition is that we can extend the definition of sine and cosine to angles that are obtuse, so angles that are beyond 90 degrees. For example, if the angle is obtuse, point P would be over here, but I could still talk about its x and y coordinate and therefore about the cosine and the sine of the angle. So I'll be using GeoGebra to construct a sine curve. What you see at the moment is the unit circle, which we also call the trig circle, and it's centered at the origin. It's a circle of radius 1. You can also see an angle of theta that is illustrated, and there is a corresponding point C that lies at the intersection of the unit circle and the terminal line of my angle. In red, you see the arc length that has been generated by moving a point that lies along the x-axis at 1, 0 all the way up to point C. At the moment, this arc length is of 0.98. So this is an angle of 0.98 radians. If I move C, of course, the arc length is larger, and right now I have an angle of 90 degrees, but in radians it's 1.57 because it corresponds to pi over 2, which is the value of this arc length. Why is it pi over 2? It's because the whole circumference of the circle is 2 pi r, but r is 1. So the circumference is 2 pi, so a quarter of that is pi over 2. So as you can see, I can get an angle of 2 pi, roughly. And this is a positive angle because I'm rotating counterclockwise. So if I would keep on rotating, I would get angles or arc length beyond 2 pi. Similarly, if I rotate, but I won't do it here because my applet doesn't allow me to do it, but if I rotate clockwise, I would get negative angles. So if I have an angle, the sine of that angle is the value of the y-coordinates at the point C. So I will illustrate this with this line segment in green. So its length at the moment corresponds to the sine of the angle. It's the length at the moment because I have values of y that are positive. But if I have an angle that's beyond pi radians or beyond 180 degrees, now the y-coordinate of this point is negative, so the sine is just the negative of the length of this segment. To construct a sine curve, what I will need is to project this arc length onto the x-axis, because on the x-axis I want to have values of the angles in radians. So what I will do is add a line segment in red here whose length is exactly the same as the arc length in red here. Now at this point here, I have the value of the angle. So as you can see, the angle is 1.13. So that means that this point is 1.13. What I need to construct the sine curve is add at this x value a y value that corresponds to this length. So what I will do is add a line segment in green here that is of the same length as the green line segment here. So in other words, this point here, which I will call D, has an x coordinate which corresponds to the angle and a y coordinate corresponding to the sine value. So overall, this point D lies on the sine curve. Now by varying the angle, the point D will trace out points that lie on the sine curve. So if I do a full rotation, I get a complete picture of what the sine function looks over the interval 0 to pi. In green you have the sine curve, and I could have used also GeoGebric to construct the cosine curve that you see in red. So it is not surprising to see that the cosine curve is just a translation of the sine curve. If I want to graph the tangent, what I have to do is at every value of theta, or let's say x here, at every x value, I need to compute the ratio of sine of x over cos of x. For example, at 0, sine is 0 and cosine is 1, so the ratio would be 0. So this point here lies on the graph of tangent. At this x value, so at this angle, the sine and the cosine value are equal. Can you guess what angle that is? That's pi over 4, because sine and cosine are both equal to square root of 2 over 2. If I compute the ratio, it is 1. So I should be getting a point here on the tangent curve. And similarly over here, sine and cosine are opposite in value, so their ratio is minus 1. So this is also a point on the tangent curve. So at every x value, what I need to do is look at sine over cosine. For instance, here you can see that sine is 1 and cosine is 0. So their ratio, sine over cosine, is undefined. But if I'm just to the left of that point, the ratio of sine over cosine will be very, very large. Once again, because sine is close to 1, but cosine will be close to 0. So I'll be dividing number close to 1 by a very, very small number. So overall, I'll get a very, very large number. So it is with no surprise that at pi over 2, tangent has an asymptote. Similarly, over here, sine is minus 1, but cosine is 0. So over here, so slightly to the right of minus pi over 2, I will get values of tangent that are very large and negative. So there's also an asymptote at minus pi over 2. In between, well, tangent is very large here, goes through these 3 points and becomes very large and negative. And the pattern repeats itself because the function is periodic. Once we've defined tangent to be sine over cosine, we can also define other functions. For example, cotangent is defined as cosine over sine, secant is 1 over cosine, and cosecant is 1 over sine. We can also derive some equalities that are true for these trigonometric functions. For example, recall that the equation of a unit circle is x squared plus y squared equals 1. This equation is obtained by applying the Pythagorean theorem. I won't explain why, but that's how it's obtained. Now recall that on a unit circle, if I have an angle and a corresponding point on the unit circle, its coordinates are the cosine and the sine of the corresponding angle. So if I replace x and y by cosine and sine, I get cosine squared plus sine squared equals 1. We call that the first Pythagorean identity. If I take this equation and divide both sides by cos square, I get another Pythagorean identity. For example, by dividing by cos square over cos square is 1, sine square over cos square is tan squared, and 1 over cos square is secant squared. So 1 plus tan squared is secant squared. Similarly, I can divide the first Pythagorean identity by sine square, and I will obtain that cotangent squared plus 1 is cosecant squared. We have seen in a previous section that the derivative of sine is cosine and that the derivative of cosine is minus sine. You have to remember that those formulas, they only hold if the angle is measured in radians. It hasn't been fully explained yet. It will be at the end of chapter 2. The formulas are completely different, or at least there is a factor that shows up in front of the expression on the right hand side if we are using angles measured in degrees, for example. In the preview activity, you will find a formula for the derivative of tangent. Now you'll have to express tangent as sine over cosine and use the quotient rule. Similarly, you can also find formulas for the derivative of secant, cosecant, and cotangent, once again using the quotient rule. And in all cases, to simplify your answer, you will need to use some of the Pythagorean identities that we discussed in this video. Thank you for watching.